Alright, so in this video we're going to look at how to write the equations for the decay of isotopes, radioactive isotopes, based on the types of emission. So remember there's different types of emission that can occur for a radioactive isotope. First one is alpha decay, where we have 2 protons and 2 neutrons, it being ejected from the isotope. Second type is beta decay, and there are 3 types of beta decay: positron emission, negatron emission, and electron capture, depending on whether a proton or neutron is being altered, or an electron. And then gamma radiation. Gamma doesn't change the size of the isotope or the number of protons. It really is just high energy photons being released. So when we look at the type of radioactive decay that occurs, we can write the equation to help us to determine what is left over, what is the remaining isotope. Alright, so let's look at our sentences and see if we can turn that into expressions and figure out what we have left. So we have nitrogen 13 undergoing electron capture. Alright, so nitrogen 13 is the mass. So if we look at a periodic table, nitrogen is 7 protons. Alright, undergoing electron capture. Electron capture is the weird one, where we have an electron, no mass, -1 charge, interacting with a proton in the nucleus to form a neutron. So this keeps our mass the same, but we're losing a proton because it's interacting with the electron, which means our isotope changes down to 6 protons, which would be a carbon. Alright, so we have a top row of numbers: 13 plus 0, still 13. 7 plus -1 is 6. So carbon 13 would be the isotope that remains. Alright, number 2. Uranium 238 undergoes alpha decay. Alright, so uranium 238 is the mass. Uranium has 92 protons, so we can find that on the periodic table. Undergoing alpha decay. So that means we're ejecting an alpha particle, which is a 4,2 alpha. Total mass of 4, 2 protons being ejected. So we need to know what isotope is left over when this happens. So we've lost a total mass of 4 from our 238, so we're down to 234. We've lost 2 protons, so we're down to 90 on the periodic table. That's thorium. Alright, so thorium 234 would be our remaining isotope. Alright, cesium 137 undergoes positron emission, so beta plus. Alright, so cesium 137 undergoing positron emission, so we're losing a positive beta particle, so 0 mass, +1 for charge. We're looking at what's left over. So we need to know how many protons in cesium. So if we look up cesium, this is 55. Alright, so if we're changing for beta positron emission means one of our protons is becoming a neutron. So we're going to lose a proton. We're going to be down to 54. Our mass stays the same. So we can look on the periodic table and find out what this is. This is xenon. Alright, so we have 1 plus 54 to give us 55. 0 plus 137, still 137. Alright, radon 222 undergoing alpha decay. Very large isotope. So radon 222 undergoes alpha decay, so our 4,2 alpha. Alright, so radon has 86 protons, so undergoing alpha decay, we're losing total 4 mass, so 218, and 2 protons, so we're down to 84, and this would be polonium. So polonium would be the isotope we have left. And then our last example, we have carbon-14 undergoing negatron emission, so this beta is negative. So we have carbon-14, carbon has 6 protons, undergoing negatron emission, so 0 mass but -1 charge for our beta particle. So negatron emission, where we have a neutron becoming a proton, which means our proton number actually goes up by 1, but our mass stays the same. So 7 protons is nitrogen. So our 7 plus -1 is 6, 14 plus 0, still 14. So no matter what type of radioactive decay is going on, the top row of our numbers, our mass numbers, should stay the same on both sides. They have to equal one another. And then our bottom row of numbers, our proton numbers, should also equal on both sides. So how do we know if an isotope is radioactive or not? There are a couple of things we can look for. In our previous video about radioactive decay, we mentioned size being a big factor. For very large isotopes, bigger than bismuth, they're all radioactive. Just because they have enormous size, their ratio of protons to neutrons is not sufficient. But isotopes that are less than 83 protons or smaller than bismuth could also be radioactive. And this radioactive instability comes from the NZ ratio, or our number of neutrons to number of protons. Alright, we have to have enough glue, enough neutrons between our protons to make the nucleus stable. So the band of stability is a graph that tries to show this relationship. So if we look at this graph, we have neutrons on our y-axis. Our x-axis is protons. So all of these little dots represent different isotopes plotted with protons and neutrons. So we can see down here at the smaller isotopes that they fall along the 1-to-1 line, or this n divided by z equals 1 line, meaning they have the same number of protons and neutrons. But once you get above calcium, which has about here 20 protons, we can see that the isotopes start veering off of that line. And the larger they get, the more they veer off that line. This indicates that they have more neutrons than protons the larger they get. They need more of those neutral glue holding the protons together. If they don't have enough neutrons, it can make the nucleus unstable. If they have too many protons, this can also happen. So we can use the band of stability to determine whether our NZ ratio is sufficient or not. So if our NZ ratio is too high or too low, below the band of stability, we know that's a radioactive isotope. The inset here shows how some of these different NZ ratios could end up causing different types of decay. So if we imagine the black circles represent stable isotopes, the blue ones here are above the stable line, meaning their NZ ratio is too high. They have too many neutrons for their protons. So what kind of decay is going to help with that? Well, if you have too many neutrons, you need to decrease your neutrons or increase your protons, or even better, do both at the same time. So these are called beta emitters. They turn neutrons into protons. Okay, so that's the type of beta decay. Below the black line, we have these yellow circles, and this indicates that these are radioactive isotopes because their NZ ratio is too small. They don't have enough neutrons compared to the number of protons they have. So what kind of decay do they do? Well, if they have too many protons and not enough neutrons, we're going to turn protons into neutrons. So these are also beta emitters, but they're going to be electron capture or positron emitters instead of negatron. Alright, and occasionally you'll have an alpha emitter in here as well. Okay, overall change in mass for those. So we're going to use this idea to determine what kind of decay these isotopes are likely to undergo based on either size or NZ ratio. So first we need to determine, are they stable or not? And if they're stable, what kind of decay? So let's look at the first one, helium-4. So it's definitely not too large. This is a small isotope. NZ ratio, we have 2 neutrons to 2 protons, so that's 1. Since it's a small isotope, an NZ ratio of 1 is perfectly fine. So this one is stable, no decay. Okay, let's look at neon. Not too large. NZ ratio, we have 8 neutrons to 10 protons. So our NZ ratio is 0.8. Okay, less than 1. So remember, the first part of the band of stability says that our NZ ratio should be 1 for these small isotopes. This one's less than 1. Alright, so less than 1. So that means we're going to have some amount of decay. So these are unstable. And since NZ ratio is too small, we need to turn protons into neutrons. So this is going to be positron emission. Alright, lead-214. Not too large, right under bismuth. Could have some amount of alpha decay. But let's see if it's stable. NZ ratio. So we need to know how many neutrons. So we're going to subtract 214 minus 82. 132 neutrons to our 82 protons. So this gives us a ratio of 1.61. Alright, so what do we think about that ratio? Let's go back and look at our band of stability. So 82 protons over here, 132 neutrons way up here. Here we go. So if we look where that is, that's up here somewhere. If we notice bismuth, which is the largest stable isotope, has a ratio of 1.52, and we're trying to get 1.61, we already know that's in too large radioactive territory. So this is unstable, and this will undergo decay. Now we can have alpha decay here, just because it's large. Our ratio is too large. We have too many neutrons for our protons. So we can also have negatron emission. Alright, let's look at calcium. Calcium 40, not too large. NZ ratio 20 to 20, so it's 1. Calcium is the largest isotope that can have this NZ ratio of 1. This is actually stable, most common form of calcium, so this one's fine. Alright, uranium-238. We already saw an example with uranium-238, so we should have an idea already that this is not stable. 92 protons, so that's above our 83 for bismuth. So this is an unstable isotope. And likely to undergo alpha decay just because it is so large. Alright, our last example, barium-123. So not larger than bismuth. We need to know NZ ratio. So let's look at how many neutrons we have. 23 minus 56. So 67 neutrons, 56 protons. So this is 1.2 for our ratio. So is that a good ratio for barium? So let's look at our graph again. So 56 protons, it's us here, 67 neutrons, puts us right up here at the top, and so we're somewhere here, it looks like, with our ratio of 1.2. So here's silver, which should be 1.28. Having a ratio of 1.2 is a little low. It puts us below the line, below the stability line. So this indicates that our NZ ratio here is too low. We don't have enough neutrons for the number of protons we have. So we need to turn some protons into neutrons again, just like we had for neon. That's positron emission. Alright, so remember for these isotopes, we want to look at the overall size. Is it too large? Larger than bismuth means it has to be radioactive. Does it have a good NZ ratio? Think about the band of stability. You don't have to memorize the band of stability. I will give you that information, but you need to know what you're looking for. Is the NZ ratio too large or too small, given the band of stability? Or is it a stable isotope?